Okay, I think audio is live, um, so generally the last 3 minutes before 10:15, I would like to set up so then we can take questions. So did you try LS data? And do you see the data directory there? Okay. Yeah, so it's just you're not in the right directory, I think. But that's a common problem. So we still have like 90 seconds, so I think we're live, so it's fine. So I tried to do something to, so please pull the updated 09, because I tried to do these steps I think Sarah might be pleased with. So like explicitly what to do, for example, to solve a very important type of problem that'll be in the exam. So just please pull the 09, the latest. So, yeah, I think the audio is okay. Yeah. So we have a 5-second delay live, right? I'm not enabling live chats or anything. So that'll be too much. So it's 10:15. Let's get started. So my plan today is to finish notebook 9. Maybe one of the most prototypical problems even the previous versions of the course has seen. So we will sort of do that both by hand, how to do it by hand, and also to use Sage Math if you want to. And then I will jump into notebook 10 because we need you guys to have some intuitive understanding at least of what convergence of limits of random variables mean, okay? Because we need that to define set estimators, right? Like confidence sets, and then do hypothesis testing. So that's the plan for today. And I also am meeting with some of the faculty who are involved in the math department with teaching STS students. So we are sort of trying to come up with a plan. So especially those students who have done multiple attempts, or more than 3 attempts maybe of the past exams, when they want to do the retake exam, we're trying to work out a system so that they can maybe do the retake exam in the old style, right, in the previous style. So it shouldn't affect you guys, okay? But I will send an email maybe end of today about those details. And you guys should kind of relax because the sample exam is going to basically integrate the different parts of the notes, okay? And if you can do the sample exam in a reasonable time, then you should be totally fine because the final exam will be very, very much a jazz on the sample exam. It won't be too complicated. Of course, there'll be one problem that separates like the 5-point students from the 4-point. It is a sort of standard thing, but it shouldn't be, you shouldn't worry so much. Okay, so let me continue. We were at the symbolic expressions for maximum likelihood estimators. Where were we last time? Yeah, so we did using Sage for basic algebra and calculus, right? So we can do solve and find roots. And the only thing is we have to define the variables, formal symbolic variables using this var thing. And then we will use this machinery to work out both by hand and by Sage Math the solution for maximum likelihood estimators. Okay. So we did this also yesterday for the Bernoulli experiment. And then we looked at the maximum likelihood principle, like what is the kind of philosophy behind this. And I told you about this notion of an oracle who has like a bag of 3 coins, and she swears that the 3 coins only have these biases of coming up heads, or 1, quarter, 3/4, and half. and you are allowed to take one coin from the bag, and you flip any number of times if you want, okay? And your task is to estimate which of the 3 coins the oracle gave you. And then by just following this numerical example, we actually said that this is reasonable, right? This way of just doing repeated trials is reasonable because you can learn the true parameter. Right? And what we saw earlier is just the continuous version of it, where the bias could be any number between 0 and 1. So that's the sort of maximum likelihood principle philosophy. So now we're going to get into maximum likelihood for the exponential lambda random variable, where we have n independent and identical trials of this random variable, which has this density function because it's continuous, and this distribution function, or CDF, cumulative distribution function, capital F. So we saw how to simulate from it last time. So now we are going to directly derive the maximum likelihood estimator. So here are the sort of 4 steps for this. So this is mostly for Sarah. I guess she isn't here today. So I think this is a good idea, right? This way you have like, what are the mechanical steps you need to solve a problem of this type? So step 1 is you obtain the expression for the log likelihood function, L sub n of lambda, right? Because first of all, you have to recognize the parameter is lambda. That's the argument to the log likelihood. And then to derive it, what do? You just set up the density, right? The joint density. So the joint density is the product. We saw this before. Now you have to substitute in the right density function for this random variable. And then you continue, right? This you can do by hand, right? So, I sort of encourage you to do this by hand. It's just too easy maybe, but these are the basic things you need, right? Basic pre-calculus notions you need. So then when you've obtained the joint density, you will basically get something like this, right? Otherwise you've gone wrong. So in the exam, for example, or possibly in the assignment too, when a problem has a lot of steps, right, where the step 2 is completely dependent on step 1, I think it's fair for me to tell you what the solution for the end of each step is, okay? So that, so step 1 will say show that or whatever, right? So you can either, you would do this in this symbolic sense or whatever, right? Or it could be, yeah, so you show some steps. It'll be clear in the notebook soon. And then in case you can't do that, then and time is running out, I suggest you move to the next step, right? Because I'm giving you the starting point for the second step. Otherwise, you guys will maybe, I don't know. You think that's fair, or is that too easy, or? Okay. All right, just because it's not really, I don't know. Okay, so yeah, that's the main. So first you get this expression, and if you write down this, it's just n log lambda minus lambda times t sub n. T sub n is just the sum of the xi's, right? This is the same statistic for the Bernoulli as well. In these simple problems, the sum of all the observations plays a crucial role. But it's a different expression, right? Bernoulli was very different. Bernoulli had parameter theta, so we had theta to the power of tn and 1 minus theta to the power of n minus tn, right, from yesterday. But this one is different. And those expressions for Bernoulli, they're actually polynomials, right? Because you have theta to the power of an integer and 1 minus theta to the power of another integer. Those are special kind of polynomials. They're called Bernstein polynomials. But anyway, we don't need all that. So step 2 is to differentiate L sub n of lambda with respect to lambda. Right? So, well, that's what I told you last time. We did the same thing. So you just have to set, you're trying to find the lambda where the slope is 0, right? So so that's all we're doing. So so you can follow these steps. This is a very simple calculus problem. Right? So you can do this by hand if you want. And what you will you can also do this by symbolic evaluation like this. So I create my lam. Remember, we don't want to override lambda, something you have to remember. Or if you want, you can do capital LAMBDA consistently everywhere. So lam, n, and t, lam, comma, n, comma, tn are our variables now, okay? Because we're going to do symbolics. So then once I've defined these variables, because those are the only things in this expression, then I define log L, or assign log L, log of lam to the n minus lam times tn, right? So now we have this exponential log likelihood as an expression, a symbolic expression, because it comes from these variables. Now I can just say log L dot diff, right? So diff is, we saw it yesterday, it'll give you the derivative, the first derivative. And then I'm just asking to show what it is, right? So it gives me this kind of ugly expression, lambda to the n minus 1 times n divided by lambda to the n minus dn. It's kind of overkill, right? But it's doing it for some algebraic computational reasons. So you can kind of eyeball this, and it's like, okay, lambda to the n is upstairs and downstairs with n minus 1, so I can cancel this, right? And get lambda. So, well, you can. So what I suggest first is we do this. So let's just see what's available, right, with the tab. So you have quite a few methods available, right? You have, diff, coefficients, collect. I mean, this is a substitute. So we will, we're not going to use everything here, but I'll show you the main ones we will be using, okay? So, so we can do the following. There's something called simplify, dot simplify method. So I'm just calling d log L dot simplify, parentheses, calling the method on it. And sorry about that. Then it gives me a simplified expression, right? Minus dn plus n over lambda. Okay? You can do this by hand. This is a simple one, but I might give you a problem where it'll take a little bit more time to do it by hand. But those problems will not be any more difficult than maximum likelihood estimation problems in any second-year engineering program in the world. So, so if you don't want to use Sage Math, that's fine too. You can do it by hand. So here is step 3, right? Now you solve for lambda in the equation by setting the first derivative equal to 0, right? So we want to find where the slope is 0. So that's just this step, right? Set it equal to 0, and this just means if and only if, right? If and only if. This is the expression, and then I just found out what this derivative is. So I put that minus dn over n lambda equals 0, and you can see directly that this is just rearrangements, couple rearrangements. So lambda is n divided by t sub n. Okay, so t sub n, remember, is just the sum of the xi's, right? The sum, sample sum. Okay, so how is this? So this we have to do a couple more steps to make sure this is the maximum likelihood estimate. But just pause for a minute and compare it with the maximum likelihood estimate for the Bernoulli experiment, right? There, our estimate was for theta. Theta was Tn over n, right? It was the sample mean. For the exponential, it's the inverse of the sample mean. It's just because we define the lambda as the rate parameter in the exponential. So now we can just, we can do the above things by hand quickly, or we can use the solve method, right? So I'm just saying solve d log L equals 0, right? This is an expression for equality, so to put 2 equals, and then comma lam. So that'll just give me my, that'll just give me lambda equals n over tn, which we did by hand. Is that clear? So you can do either or, and there will be problems in sort of real world where you may not be able to use your hands anymore. I mean, by pencil paper. And there will be problems where you can use the symbolic machinery, but the symbolic machinery will output like, I don't know, several hundred pages of expressions, which is equally crazy. So, I mean, then you do other things, right? But yeah. So there's no silver bullet for everything. So this is the sort of last step, and this step is mainly to make sure that in case the log likelihood is behaved in a weird way, what if we found the minimum, right? So we have to make sure that the second derivative of the log likelihood function is negative at the solution, right, at the slope being 0. So that's the last step. So show that this is indeed a maximum by checking the second derivative d by d lambda of d by d lambda ln of lambda is negative at this lambda. Right. So this is again just some basic calculus. It's very simple. You can just get that this is minus n over lambda squared. So that's the second derivative. Now you can kind of stop there and be quick. And if you know that lambda is positive, right? Parameter has to be greater than 0. And n is just an integer, right? The 1 sample or 2 sample. So minus n over lambda squared will always be negative, right? But that's a very peculiar thing about this density because it's so simple, right? It just has a unique maximum. That may not necessarily be the case, right? So problems where, people use, say, the heights of ocean waves to build some offshore multi-purpose power plant has a 3-parameter family of some what are called heavy tail events. So you have to build the structures, right? I think Norwegians are really good at this. You have to make sure that the structures and the concrete buoys and everything can withstand like a very high probability ocean crash, right? So then you need to know what is the historical behavior of ocean wave heights and pressure. So this is more like, I don't know, you guys don't do this. I guess this is more like construction, civil engineering. And so what these engineers will have is like some models for using historical data of ocean dynamics. They will have a model, which usually will have 3 or more parameters. And then they will do maximum likelihood estimation from the data, and then use those estimates to compute that the probability that this structure that's mining or oil or whatever in this particular location under these conditions is not going to have to be rebuilt in the next 150 years or something. So there's these guarantees, right? I mean, probabilistic guarantees. So in problems like that, you won't have this very simple thing. You have to go further down and check that the actual solution is, the second derivative evaluated at this actual solution is indeed negative. So I will just show those steps here. So we basically have this. What we really need to do is to, this kind of expression, evaluate the second derivative at lambda equals lambda n hat, right? Calculus notation. So now we are saying, okay, my maximum likelihood estimate is n over Tn. I'm going to take this as my estimate, and I'm going to make sure it's really a maximum. That's what I'm doing here. Right? So you can do the same thing by hand, and boom, boom, boom. You get minus t sub n squared over n, right? Because I simply substitute in my n over Tn into the expression for the second derivative, and I get minus t sub n squared over n. Which is cool, right? So this guy is always negative, right? Even, forget about the parameters, right? So when we evaluate the second derivative of the log likelihood function at the maximum likelihood estimate, we say is n over Tn, then we get this. This is always negative because t sub n, right, which is the sum of the xi's, is going to be positive, right? Because the exponential random variable, right, takes values, the support is in the positive half line, right? It's actually a time, right? It cannot be negative. So that's fine. So this guy will be positive. And then, oh crap, that's a type. Oh yeah, I shouldn't put dollar signs here. So this is just saying the sample size is greater than or equal to 1. Okay? So in this case, so you see there's this pink warning. All right. Yeah. So then so these are the 4 steps. So what we've shown now with these 4 steps is that the maximum likelihood estimate. So I try to be consistent, but when I use estimate, I put a little e, okay, because it's a realization, remember? And if it's an estimator, I put a capital E, right? I'll try to be consistent. But this is for conceptual reason, right? Is indeed lambda n hat, which is n over Tn, and just inverse of the sample mean. So I say you can expect such a problem in the exam and probably assignment 3 also, okay? I'll maybe try to embed one just below. But here's how we can do all of this very quickly. So your main thing is to figure out this expression, right? And this also, there are steps to do this, right? You can, so log L is this. D log L is just this, let's simplify. And D2 log L is just, you put F2 here for the second derivative. That's it, simplify. So then here comes the, so then it says D2 log L is n minus 1 n lambda squared. That's not really good. There's another method called full simplify, okay? So you can use this as well directly. So full simplify does the maximum possible reduction, right? In some underlying stuff, right? So this is now minus n over lambda squared. So this is, again, you can directly work with this. So finally, to check that the second, so we know our lambda is n over tn, so there's a method called subs for substitute. So you can just take this expression and substitute in, right? It's just like doing by hand. So you can also check like this. What you did by hand is correct. And in the sort of exam, you can just directly do these things, okay? Okay, so that's what we got by hand and by computer. Yeah, and if you know how to do this, so I can always go like this, Control V dot subs question mark, right? So I sort of, you can see there's more complicated problems. It tells you how to do substitutions. So there's relational expressions, all sorts of things. So you can use this in your other math courses as well. Here we won't really go beyond these 4 steps, okay? So what is it called? Use the source, Luke. You know this joke? Oh man, use the force. You know this? Okay, so all right, so now let's get into a more interesting analysis of exponential, right? So we're going to use New Zealand earthquakes as our example. So what we will do is obtain inter-earthquake times, right? So there is a file in your data folder, and we're going to essentially do some sort of statistical processing of the raw timestamps, and then we are going to get the time of the actual earthquake is what's in the file. What we have to do is order the times, because sometimes these sensors are embedded all over New Zealand. Actually, there's a whole global database anyone can plug in 1 week late. I think it's the courtesy of the US Geological Service. So you can actually see every earthquake all over the planet, over Google Earth visualizations, right? Maybe I'll try and find that later for fun. So you can actually see it happening, but it's a 1 week delay, right? So, for example, like 2 months ago, or actually December last year, there was some really amazing essentially regression, but like involving lots of machines in the cloud, where they try to use all this historical data and they're able to predict where the next earthquake will happen with a very high accuracy. It's scary. Because the mathematical problem is non-trivial, right? It's an incredibly complicated problem, right? Because there are tectonic plates underneath, and if there's a big boom in Japan, there will be one in New Zealand and Chile, because there are all these. So it's an incredibly coupled problem. But by using really deep historical data, they've been able to do some predictions using essentially, regressions, which are these days called AI algorithms, because they're just too big a model. So let's go with our world here. So we have, this is what you should see. Every time when I give you read some data file, you should make sure that %/sh ls data is actually there. So, so what we are going to do now is this one, earthquake small.csv. and then earthquakes.csv, right? So if you don't have earthquakes.csv, you have to unzip it. I think we did it before when we looked at magnitudes. Right. So this is how the file looks, you see. So what I've done here in the last one is I did a word count, WC-L of this file, of the full file. So it has 21,017 lines in it. Okay, it's a kind of a big file. And then I'm doing head -3. Give me the top 3 lines of that file, right? This is just from week 1 on bash. So these are the top 3 lines, right? So the first line is clearly the row header, right? Public ID, event type, origin time, and so on. So origin time is, I think, our main one. We want to know the time of origin of that quake, right? And that's this here. You see, it's 2018 minus or dash 05 dash 17 T12 1935 blah blah blah. So there are so many date-time formats. So one of the main things you will want to do, even to fit a simple exponential, is to extract this time stuff. So this I will go do in kind of a hurry, right? So you can kind of chase this on YouTube. If I ask any questions in assignment with this stuff, you will just have to copy paste something, so you don't have to worry about it. But I'll go a little bit faster, okay? So we're going to use Python libraries, date, time, and time, okay? And you can chase the docs here. So from datetime, we import datetime. So it's the whole module. Now I'm going to just, start creating a little list of strings for dates. Right? So let's start with 7 to 2011 and so on. So there's a month, date, year. Right? So this is the American format. So then date times list. What I'm going to do now is I'm going to use this datetime module we called, right? This is already in our at our disposal. It has a method called strip time or strp time. So this method takes a format string, takes a format that we specify, and then it'll extract or strip it from the string. So this is the format. So we are saying it's month, %month, / %date / %year. So if you ask, how am I figuring out all this? I spent a few hours going in through these libraries. So you don't have to do that right now, but you can in the future if you want. So now I'm doing a list comprehension. So this whole block is going to give me some strip time from each string in this format, which I know. And then I'm just doing for TS in the string dates. So it's just going to list comprehend and give me this back. Right? That's all I've done. So let's display this. Datetime list is now date.datetime, and it's pulled the year, month, day. Okay, and it's automatically put zeros for these other things, right? For hour and minutes, because that's information isn't there. So, but we want to convert these datetime objects into a number, because these are actually Python, datetime objects. So, so into a number, right? And then we're going to use this Unix time number. It's one convention. So I'm going to import time. So it's another library we need. So I'm going to do time.mk make time, mk time. And then I'm going to take this ds, which is in this list. So, and I'm going to do ds.time tuple, because there's actually a time tuple. And then I'm simply going to get these Unix values for time. This is called a Unix time number. I think it starts in 1971 or something like this. Okay, so now we basically have a global mapping to the Unix time world. So this is how you can take all kinds of formats. This is one way, all kinds of formats to map to the same calendar time sort of Unix time universe. Right? So then now we can do the following. I'll just do all of it at once. So yeah. Okay, so then we use parse in dateutils.parser to try to auto-convert common time formats, right? So lots and lots of time formats are used, especially in historical files. This is the same thing if you download similar data from Swedish public databases. It'll have a slightly different format, but most likely dateutil.parser will have this stuff. So now I basically do this, import parse, and then this one you see, now we're going into our sort of real world, right? So we're going to parse it using this format, right? This is one of our examples from the earthquake timestamps, right? So the real file, remember, has something like this. So where is it? Yeah, right here. So we're pulling this guy, okay? And then seeing if it can handle that. That's all I'm doing here. And see if the time tuple is there. And then now it says time.struct time is, time year is 2018, months is 5, 17 days, 12 hours, 19 minutes, 35 seconds, and so on. Right? Yeah, and there's yeah, the day of the year and a bunch of stuff. Okay, so we can just use parse in a list comp like this, and this is essentially getting this information back. So finally, we can do all of this. You know, all these little steps I'm showing you. I'm kind of showing you now just for two timestamps from our earthquake data file, right? Instead of one. But if you can do two, then there you go. So I've parsed it, and so now this is it, right? So once you get that, then all I have to do is with open data earthquakes.csv sf, I have a reader, and then I'm splitting it by end of line characters, because this is a file where there's an end of line, right? /n is end of line. So I'm breaking it line by line, and I'm going to turn that into a list. So that's my data list. So there's 21,018 elements. And let's make sure that there is exactly the same number when we did WC-L, 21017. Okay, and what did we have here? 21018. Maybe there's an end of line thing, I don't know. Okay, so so let's look at the first row. That's just the headers. The second row with index 1, that's the first data row. Oh yeah, this is one. So there's a culprit, right? Looks like the last line is empty. So so now the data list -2 is going to give me the second last line. The second last line looks okay, right? I mean, it's not empty. So anyway, we've seen these try catches on the Powerball thing, so I don't want to get too involved in this, but this is essentially a block, right? So now we basically have all the stuff we need, every little bit we saw before in 3 different imports. And then I have my list empty, my data accumulator list. And then I'm just going for every data element from the first index, which means we skip the first line, and then up to -1, which means we skip the last line. So we only go to the second last line, right? Because we just saw that that's how the data is. So this is not like super robust, but again, this is not a computer science class, so we don't have to worry too much. So we just have to do a little bit of try and accept, right? Because we have to make sure that we can do the castings correctly. So what's being done here, so you saw my type time will come out, but what we have to do is we have to turn this Unix time, you know, this big floating point number we saw. Sorry, we have to make sure that the Unix thing we got is actually a float. So we cast it into a float, and then we append it, right? Append the process timestamp to my float data, and yeah, when there's a type error, I report it. So at the end of this, so you don't have to worry too much about this. Okay. So then, except to be able to use it, right? Just copy, paste, and use it. So then my data accumulator list is now like this. So I'm only looking at the first 5 lines, and everything looks okay, right? So I have my, so what did I grab? I grabbed the longitude, latitude, magnitude, and depth. So we saw these things before. So now we're going to also grab, and what we added is this timestamp in the end, right? That's our main extra bit here. So this is the Unix timestamp. So all this stuff you've seen above, right, is kind of like slapping together little bits of cells into one cell, right? That's so that you understand all the different components coming together. So when you fully understand this and it's pretty robust, you usually turn it into a function, right? So this is what you learned in your Python class, like writing functions. So all I did is just, wrapped all these bits and bobs into a function. But the important thing, like someone yesterday had problems with the assignment, when you take a block of code like this and turn it into a function, then you have to add 4 spaces everywhere, right? This is Python white space blocking rule. So if you don't do it, then the function complains, right? Because it's not a function. So that's all I've done here, you see, boom, 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 boom. I think assignment 2, problem 3 is something like this. You're supposed to grab the, what is that thing called? Swedish election data. It was done for the party, but it's in one of these blocks without a function. You're just kind of literally supposed to grab it, turn it into a function, and put 4 white spaces everywhere, and then change the row number from 2 to 3 or 2 to 4 or something. That's basically it. So anyway, this is all I've done. So now I do a little bit more, like I turn this into a NumPy array, right? Because I want to do numerical linear algebra, well, some simple things like even Kim-Sim and so on. For regression, we will do a bit more, right? So that's why we get into NumPy, because I want you to use things you're learning in linear algebra too, right? Okay, so my processed array is now, it's going to take a while because it's several lines, okay, about 1.5 seconds. And then I can ask what's the shape. So it has 21,016 rows and 5 columns. That's my NumPy array, right, or matrix. So there you go. And you can see the first 5, right? And it all looks okay. So you have longitude, latitude, magnitude, depth, and times. Okay. So here is the next step. We're just focusing on the last column, right? Because we want to see if the exponential lambda random variable, how well it fits this model, right? So there are these time events. Right, so an earthquake happens here, and boom, boom, and boom, and so on. Of course, each one of those, the actual magnitude, there's another 3-dimension, right? Latitude, longitude, and magnitude. So that's like the map, New Zealand, and the magnitude is how heavy duty it is on the Richter scale, right? I mean, when the big earthquake happened in 2011, I was on the 7th floor in the math department called the Erskine building. And everyone is supposed to go under the table and hide, but I just had my tea, like I was standing up and it just happened and I was just looking, these lamps sort of like swinging like this. And when the lamp sort of hits the actual walls, I started like standing like this. And all my C++ books, the hardbound books, they started coming straight out and I was boom, 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 boom. And then I fielded my laptop, but anyway. Yeah, it was a very scary time because the aftershocks continued for about 3 years and, it was pretty hard on. So anyway, this is what we've done, right? So I've taken the inter-earthquake times. So I want to get the inter-earthquake times from the quake times. So the problem is I need to make sure that everything is sorted first. So I think I handled the sorting earlier because data can arrive from, like sensors in different time order, right? Because actually the event gets recorded maybe because of internet traffic delays. They may come to the repository, the data repository in, later, right? So that's why the timestamps come with the file. So then you have to order it by timestamps. Right? So once you've ordered it, I have to now make sure that I do the consecutive differences, right? Then I get the inter-earthquake time. So this is say T1, this is T2. So what I'm really after is say this is 0 whenever I start. So then I go T1 minus 0. This is just T2 minus T1 and so on. That's what I mean by inter-earthquake times. That's all I'm doing here by a simple list comprehension, right? Okay, so and then when I plug in just the first several values, I get, I get my yeah. I need to check if I'm doing this correctly. I may have to do the sorting upstairs. I'm doing a sorting here. Anyway, let's continue. So then this becomes the inter-earthquake times, right?
Could you pull down the board?
Oh yeah, thanks. Yeah. So now we have our data, which is now ready to be fitted using our exponential model, right? Because now in our model, just like the bus arrival time example I told you, we're going to say that this is, of course, completely not sensible model, right? Earthquakes are not occurring IID exponential. But let's model it like that. Why not? That's just assumption. So then the question is, what is the best fitting lambda sub n hat, the maximum likely estimate for under this model for this data? Okay. And we have to get into hypothesis testing to see if this is good enough and things like this, but let's come to that sequel. So we have 2000, 21,015 inter-earthquake times. And the step 2 is now modeling earthquakes. So we're just looking at the first 10, and those are the inter-earthquake times. And then I'm getting the inter-earthquake time in seconds, so that's my mean. So this is the sample mean in minutes. So, on average, right, the time between earthquakes in New Zealand is every 24 minutes. It's a lot. I mean, it's not like heavy duty, high magnitude because I've got everything, but these are measurable. And then the sample variance is just that, and we're just using NumPy for all of this. It's convenient. Okay, and the inter-quakes second standard deviation is this. Okay, that's just from the raw data. So now we can say, let us make this overly simplistic model. So let's take the sum of the inter-quakes times in seconds. So that's a big number. And we know, we just derived the maximum likelihood estimate, right? Maximum likelihood estimate is just n divided by t sub n, right? So we find the sum, and then we can just put n divided by t sub n. But first, let's look at the data, right? So this is just a count histogram for inter-quake times in seconds. So here's the inter-quake times in seconds downstairs. And this is raw data, right? And just the counts. It definitely looks kind of like exponential, right? Just so it's not unreasonable to model. And you can change the bins if you want to be a proper guy. Like, you guys are supposed to do this kind of things like since the 1970s. So this is called exploratory data analysis, right? So you sort of explore the data, and then you sort of think about it. And this is due to Tukey, right? He's a very famous statistician. So you kind of, I already did this, so I know the exponential is not a bad idea. So, but if it's like this, boom, and then boom, boom, weird patterns, exponential will be bad idea, right? And there are others. There are other models you can use. But okay, so our single best guess or point estimate, lambda sub n hat of the unknown lambda star. So in our model, we're saying that it's IID distributed according to some unknown lambda star. And we're going to hunt down this lambda star or find a point estimate of it with the maximum likelihood estimate. That's all we're doing. So it's n over Tn. And so this is our best guess in seconds. Best guess is the MLE here. This is the rate parameter, right? So it's just inverse of the mean. It's nothing really going on. Okay, so yeah, it's just the mean, inverse of the mean. Okay, so now what about converting our data to give the interquake times in minutes rather than seconds? Then all you have to do is just do a division, and you can get it in minutes, right? 60 seconds per minute. So yeah, so now we have our mean and our 1 over the MLE is the same, but in units of minutes. Okay, so now what is the relationship between the best guess values, or the MLE, for lambda star when we are measuring time in different units? Right? Does this fit with the idea of lambda as a rate? Right. So this, I think, should ring bells, because that is the exponential. The last problem in assignment 2, right, is about this, the scale. It's, so remember, you have a toggle, and if you change lambda, something happens. It looks like nothing happens, but some things change in the x-axis. So it's just, it's a rate parameter, so it controls the scale. Okay, so we have 1 more minute. So this is just the picture in minutes. So now I just, there's a lot of plots I've done. If you guys want to play around how I'm doing the plots, you can do this. This is not like requirement. Matplotlib is very powerful, so it's heavily used in data science these days. And I sort of encourage you to get into it. And here's just the count histogram for the inter-earthquake times. And I'm just sort of showing you how to plot a line on the count histograms. So if you want to plot the PDF of the estimated lambda next to the density of the data, you can kind of see it by eye. So we'll probably come back to that later. This is for you to practice how to use symbolic expressions and stuff. So it's just a you try. There's a feature tour. As I said, I'll come back to regression at the very end. So before you fly off, I have one last 30 seconds. Let me show you, and then I'll. So this is a question people are asking, right? So this course was taught in R. Why are you doing it in Python? I told Elizabeth I can do it in MATLAB, Python, or R, but you have to choose. I can't do all. I was advised to do it in MATLAB by the previous person that was teaching it, because you guys know MATLAB. But then the MATLAB is being phased out of the engineering program here, and Python is introduced. So then I chose Sage Math, because in Sage Math, you can also do R, right? I'll do like little snippets. So you do %R, and you're back, boom, in R kernel, right? So I said, I'm from India, right? You can speak any language you want. Just have to solve the problem. Right? And you do want to use R. We use R at work, because there are so many time series libraries that people have spent hundreds of thousands of hours writing. You don't want to reinvent it. You just do %R and jump into it. And Sage Math is okay for single machine computations. When you do real stuff, there are similar notebook environments, same Jupyter environment for distributed computations. There, people who called data scientists today, or for example, or applied statisticians with a lot of computer science, they babble in 4 languages. The standard exams, the industry standard exams, are 4 languages, right? I mean, so I'm kind of preparing you for this, right? For those of you who want to go into the machine learning track. So we'll start 2 minutes late.
How do you mean you switch to R?
I'll show you here. 5, 6, 7. So let me just. So switching to R is pretty easy. So you just do, and then.
Okay, so.
I don't know. I forgot R now. Do you say hi like this in R, or I think it's a function, right? Let's try this. So you're not. So there's now R kernel running.
I have a question for the assignment. So it says you can import you may not import libraries that have not been introduced before so far. And I'm importing this one for string management.
Yeah, we use regular expressions.
Okay, we use
Yeah. I mean, I just don't want you to, like, if you're really good on your machine, you can import pandas, all sorts of other Python packages on that path. You know, it'll get too complex for me to feel it, right? So that's why I'm keeping the number of packages minimal.
And then the fourth one, the